Okay, for my bonus question, I will be explaining how to do question number 1. Okay, so the first question is true or false, right? So for any non-zero vector v, there are infinitely many vectors u in R3 such that a projection of v onto u is equal to u, right? So the key takeaways of this question is that, first of all, it's a unit vector, so the magnitude of u will be equal to 1, right? So the given question is that the projection of v onto u is equal to u, right? So we can put it into this form such that u dot, using the formula of vector projections, u dot v divided by the magnitude of v squared times v is equal to u, right? So we can assume that u dot v is a scalar, right? Because this is if you dot u dot v will give you a scalar, and dividing it by the magnitude is a scalar, so a scalar divided by scalar is just going to be a scalar, right? So u is going to be equal to a scalar times v, right? Let's just assume that the scalar is a, right? So the magnitude of a times the times v, right, is going to be equal to 1. Since the magnitude of u is equal to 1, this magnitude is also going to be 1. So we can take the a out. The absolute value of a times the magnitude of v is going to be equal to 1, right? So the magnitude or the absolute value of a is going to be equal to 1 over the magnitude of v, right? And a can be equal to v divided by v, because, or no, u is going to be this times v, because we can sub a back into this equation where a is this, right? So since we found out that a is 1 divided by the magnitude of v, right, it's going to be v times the magnitude of v and the negative value also, because this is an absolute value, so it's going to be plus and minus. Therefore, u cannot be infinitely many vectors. It can only be these two vectors, right? For example, right, if we have 1, 0, 0, we put all this, right, we do the projection of v onto u is equal to u, right? So we use the formula again, right? And this time we can put that, since that we know v, right? We know v, so u dot v is going to be equal to u1 times v1. v1 is 0, right? Or 1, right? So it's just going to be u1, right? And v2 and v3 are 0, so the dot product is also going to be 0 for these two, right? And divided by the magnitude of v squared. So v squared is 1, right? So the magnitude of v squared is 1, right? Times 1, 0, 0, right? So u dot u1 dot or u1 into 1, 0, 0 is going to be u1, 0, 0, right? So this is going to be equal to u, right? And then if we take the magnitude of u, right, the magnitude should be equal to 1, right? So u1 squared plus 0 squared plus 0 squared is equal to u1 squared. U1 squared is equal to 1, right? So u1 can be plus or minus 1, and there's only two possible vectors u1 can be, right? There's not infinitely many. It's just two vectors, 2 unit vectors, right? So this statement is false. For the part B of question 1, it says let U, V, and W be 3 mutually orthogonal non-zero vectors in Rn. Then U and any linear combination of V and W are orthogonal, true or false. So if U, V, and W are mutually orthogonal, right, then U dot V is going to be equal to 0, U dot W is going to be equal to 0, and V dot W is going to be equal to 0, right? And now, for the linear combination of V and W, right, so U dot we want to prove that U and this are orthogonal. So if U and a linear combination of V and W are orthogonal, then the dot product is going to be equal to 0, right? So let A and B be scalars, right? And basically from the property of we can take A out, right? And we can multiply U in, right? We can multiply U into the we can distribute it because of the the properties of the dot product. We can distribute U into both this and this, right? So U dot V times the scalar A plus B times U dot W is equal to 0. And from our original equations, U dot V is equal to 0 because U and V are orthogonal. And this is going to be 0, right? And U dot W is also equal to 0. So both are going to be equal to 0. Therefore, U is orthogonal to any linear combination of V and W. Right? So that's true. The next question states that there exist two unit vectors U and V in R squared such that the magnitude of U plus V, right, is equal to square root of 5. So if we have the magnitude of U plus V is equal to square root of 5, then the magnitude of U plus V squared is equal to 5, right? And if we have from the equation of A plus B, all right, the magnitude of A plus B squared, right, we can distribute this into U squared, the magnitude of U squared plus the magnitude of V squared plus 2UV, right, is equal to 5, right? And from the question, we are given that U and V are unit vectors. So U, the magnitude of U is 1, and the magnitude of V is 1, right? And basically, so we get that the magnitude of U squared plus the magnitude of V squared plus 2U dot V is equal to 5. So this is 1, this is 1, right? So 2U dot V is equal to 5, or is equal to 3, right? Because 1 gets cancelled. And U dot V is equal to 3 divided by 2, right? And so U dot V is equal to the magnitude of U times the magnitude of V cosine theta, right? And in this case, the magnitude of U is 1, the magnitude of V is 1. So U dot V is going to be equal to cos theta. And cos theta is equal to 3 by 2, right? But cos theta cannot be 3 by 2 since the range of cos theta is between -1 and 1, right? So there exists no unit vectors uv for which u plus v is equal to square root 5. Therefore, it's false. The statement is false. For D, for any two vectors u and v in R3, there exists a unique vector w that is orthogonal to both u and v. This is false. If u and v are parallel, then there are infinitely many vectors orthogonal to u and v. So u dot w is equal to 0, right? V dot w is equal to 0, right? So for example, if we have 1, 0, 0 and 2, 0, 0, these vectors are parallel, right? Then in this case, w can be either w can be 0, 1 or 0, 2 or even 0, 0, 1, right? If you take the dot product of any of these guarantee that w is orthogonal to u and v, right? And w is not unique, right? So therefore the statement is false.